All right, this is 4/8, day 2. It's got a couple new things in there that we're going to do. This, really the first and the last, are the skills that are a little new. And what we're after here is to just get a table of data and to see if we could write a trig function that's going to approximate or model the data in the table. Okay, so what I want you to think when you see this is A, B, C, and D. Okay, those are the 4 different numbers as far as shifts and stretches that we could kind of mess around with to get a sine, and we're just looking at sine or cosine here. Okay, we're not going to write any, you know, if you're coming up with A, B, and C, and D, we're not going to do it with any others, with tangent or cotangent or anything like that. Here's what you really need to get out of the table, because some of these measurements that we have to find work really well with formulas, and then one in particular kind of doesn't. But A, if you can look at the table and figure out, in this case, the max and the minimum water depth, A, or the amplitude, is always your max minus your min over 2, or in this case 4.15. Okay, really, really straightforward number to get. B is a little bit trickier, but you can still really get it from a formula. I look at the table and it looks like at midnight right here we're sitting at low tide, and because the water depth at the end of the dock is minimal, and we're there again at noon. Okay, we're there at both. Okay, 2 pi divided by B has to equal our period. Okay, we can use a formula here. We do have some solving that we have to do. It's not like A, where you can just plug in the numbers and simplify, but you can look at the table and see, all right, it looks like the period should be 12 hours, you know, because I saw a kind of difference between, like a really good thing to go off of in a table is difference between maximum and difference between minimums. Either one, okay? It'll be the same. If it's a sine or a cosine curve that fits that data, they'll be the same. And it looks like 12 hours. Well, then I can multiply both sides by B, and I would see that 2 pi has to equal 12b. I divide both sides by 12, and we're getting really close. I'm going to come back over here to put my final answer when it's simplified. And B needs to be pi over 6. Okay? C is our horizontal shift, and it's tough. Okay? I kind of got to think this through, and the first thing you should look at is, do you want the graph shifted? Okay, or could I just say that, you know, if I'm going off of time, am I okay with saying that t equals 0 is midnight? Well, if we did that, then that would mean t equals 1 is 1 a.m., t equals 2 is 2 a.m., and so on. And that honestly seems to be a pretty good fit. Okay? So I'm going to say, all right, let's not shift it at all. Let's say that c is 0. Okay? And then I do want to say that t equals 0 is midnight. And then the other thing I'm going to do with my domain here to make sure this kind of makes sense is the tide will come in and out twice in a day. So I'm just going to say, like, for the domain, go 0 to 24, right? And then it's going to start over again, but let's basically say that our function stops after 24, because it would just repeat again, but I would only be interested if I were looking at this graphically to look at 2 periods. Okay. D is a really slick one. This is your vertical shift, but again, it's very formula friendly. A max plus min over 2, and you should get that it's about 7.15. Okay? I've got A, B, C, and D. Okay? Now, I find, as you start working on these, what I really see a lot of is this part goes okay. Right? And then it's kind of like, all right, where do we go from here? Or you kind of get the sense that we're done. All right? And we're not quite yet if we want to actually write the equation. Okay, it's the water depth based off of time. Okay, the other huge thing we got to figure out is, do we want to use a sine curve or a cosine curve? Okay, we decided not to shift it horizontally, so I'm looking over here at where it starts. It's way down at the minimum. All right, so we got to think way back to when we saw sine and cosine. They had like a really fundamental difference about where they started. A sine curve would always start in the middle, whereas a cosine curve typically would start at the top, but we could make one little adjustment for it to start on the bottom. Okay, if we put a negative sign out front. So I'd go negative 4.15, there's A. Okay, using a cosine curve, that'll start it down at the bottom where I want it. B always goes with our x variable, or t in this case. Cosine of pi over 6 times t plus 7.15. Okay, that cosine curve would represent, like all those little times in between that we don't have. This would give us really, really good approximations for what's going on with the water depth at that particular time of day. Now, I'm out of room, but if you wanted just another, kind of the logical next place or next step to take this problem, graph that. See if you could take the equation that we just came up with, and could you graph 2 periods? It's going to be a big test topic, so if you want to do that on your own, feel free, and we could talk about it more in class. All right, this one's has a couple little differences to it. Again, it's kind of got this element of writing a function. It's not a long derivation to get this equation, but it in some ways is a little bit tricky. What the problem is saying is you've got this camera down here, all right, and this space shuttle that's taking off is on ground level, and the camera is looking straight ahead. Okay, so we'd say it's like at a 0-degree angle. And then as the shuttle takes off, we're calling its height above the ground S, the angle is going to increase to make sure that it's still filming the shuttle as it's taking off. Okay? We want a function, and think about it like this. If we're saying theta as a function of S, think of it in terms of x and y like that. We want to say we could plug in the height of a shuttle, like where the shuttle's at. Okay, and you can kind of see in part B that's where it's going, is, hey, what would the angle be at 300 meters? What would it be at 1,200 meters? Okay, but we want to plug in any height the shuttle's at and then know here is where the camera angle should be if it's still going to film properly. Okay, so we're definitely looking at this right triangle from this angle in the bottom corner, right, the angle of the camera with the ground. The height of the shuttle is like the opposite side, and then 750 is definitely going to be a side that we use because it's the only one that we have. The hypotenuse doesn't seem very relevant, and the other side of the triangle formed by the height of the shuttle is going to be constantly changing. So for part A, to just get something in writing, even though this isn't technically a function yet, I could say tangent of our camera angle is the height of the shuttle over 750. Now you look at that and see, hey, we've got 2 variables, but you know what? That's okay. we actually want that because think of x and y. We want this to be like a function, so we plug a number in, get a number out. Okay, the only thing we have to adjust here is if it's going to be theta as a function of s, theta needs to be by itself. And again, use this analogy of thinking of theta as our y variable. Okay? Anytime we were working with functions, we always love it when y is all by itself. Okay? Now to do that, I would just have to take an inverse tangent. That would cancel the tangent, and then I'd have to do it to the other side. And I would get inverse tangent of s over 750. And there you have it. Okay, a tricky little derivation, but not a long one. What we have there is you could take s, okay, any height of the shuttle that you want, okay, after its launch, plug it in, divide by 750, take the inverse tangent, and you've got the angle that the camera should be at. In part B, all that's going on is you're just plugging in two of them. Okay, when S is 300, this would obviously be a calculator component. You really, if you wanted to be efficient, you could go back and use that table feature on the graphing calculator and kind of get both at the same time. This would just have to go into your y equals. But you're just finding two of them, so it's not that much work to just plug them in. At 300 meters, it should be at about 21.8 degrees. If S was 1200, the shuttle's higher, so this angle should increase, and it certainly does. At that point, theta would have to be about 58 degrees. All right, really two problems to go here. This one is, again, kind of a miscellaneous type of geometry problem here. We talked in an earlier lesson about this whole angle of either repose or repose. I'm not exactly sure how it's pronounced, but it's this idea when, like, typically something that's mined or like an agriculture product that has been kind of produced, it's often stored in really large piles, and they kind of fit a cone shape, but what product it is can determine exactly, like, you know, how tall is it versus how wide is it. So here's what we have. I'm going to draw a triangle, and this is just kind of the profile shot of the cone. So there would be this. I don't need this other side because it's just going to be a mirror image. Okay, but what we know is, first of all, that's the angle that we're after. It told us that the diameter of the cone is 82 feet, so I'm going to split it up into 2 halves of 41, and then our height right here of our pile of corn is 20 feet. Relatively simple kind of concept behind the question. We are looking for the angle. That's what we're trying to find here. Really, my only option is to go with tangent, and to say that tan of our angle is 20 over 41. And like the last one, we actually end up using an inverse tangent. I'd use the calculator to help me out and see that that angle is 26 degrees. Okay? At this point, if more corn were to be added to the pile, the angle, and this is why it's a big thing to find, isn't going to change. Right? The pile is going to get bigger, it's going to get wider at the base, and it's going to get taller, but the angle is going to stay at 26 degrees. So in part B, a bunch more corn is added. And here's what we know has happened. first of all, that the angle doesn't change. The base is now 100 feet wide, so those both need to change to 50. And then the height's no longer 20. It's just unknown. Okay? But now as we set up our formula, we could say tangent of 26 degrees because theta is a constant, right? We found it in part A. And now we're saying the opposite is h, the adjacent is 50. Just one step to solve it. H is going to be 50 times tangent of 26. With a little help from a calculator, you should see that the new height would be about 24.4 feet. Okay, which is interesting. I mean, you know, the piles seem to get a lot wider. It got 18 feet wider at the base, 82 to 100, but it only got like right around 4.5 feet taller. All right, this one is going to be really, really similar to the first one we did. I'm just going to do one of them. Actually, if I have room, I'd like to graph this one as well. I'm just going to do Tallahassee. If you want to do the Chicago one, it's a homework problem, so you know, feel free. Same place to start here. Let's think A, B, C, and D. Again, a huge, huge thing is to go through your table here. And can you make sure you get your minimum and maximum? Okay. Looks like January is the coldest. This is a weather model, by the way. We're just getting climate data on two cities, Tallahassee and Chicago. We've got our max and min, okay, and the other thing I'm looking at in my table, really two other things that are going to affect the equation I'm going to write is this goes from 1 to 12. So it looks pretty clear that we want our period to be 12 months, which is actually going to be pretty darn similar to the water depth problem that we did at the beginning, because there it was hours, but the period was still 12. And here's the other thing. We were okay with that problem starting at t equals 0, the water depth problem. This one we'd like to start at 1. Okay, so that's going to come up when I get to C. All right, A is always quite nice to work with. .1, okay. 2 pi over b equals 12. Now, make sure we're clear here. Showing your steps to solve this would be really important. I'll let it go this time because if you look back to, again, the water depth problem, we did the same steps to solve it, 15 minutes ago. So if the numbers were different, I would be very particular to solve it again. All right, C is going to be 1, right? And that was going off of this over here. I want my graph, and there's not really a formula to go to here, but when I think about starting at 1, I want it shifted 1 unit right. Okay? So I'm going to make C1, and then D, this is max plus min over 2, and we'd get 77.9. Okay? Excuse me. All right, time to put the whole thing together here. I'm just going to call it X and Y. I think it calls it like big T, little t, or something like that. I'm just going to go X and Y. Again, to write the whole equation, we need to decide sine or cosine. Okay? And again, what you're pretty safe to go off to is look at where you chose to start it. Top, bottom, or middle. Okay? What you really want to start with is if you rule out the middle, then we're saying this is not going to be a sine curve. Top or bottom potentially could be a cosine, and that's what we're going to have here. Okay? Again, to put it at the bottom, I have to do the negative. So negative 14.1 cosine. This part gets really, really picky. With my vertical shift, I have to do pi over 6. And then x minus 1, that will give me my shift of 1 unit right in parentheses. Plus 77.9, and that's going to be a pretty darn good weather model. And I do just very quickly want to graph one period. Okay, it's actually not too bad to do with the help of the table, because really what I'd be after here is first period will start at 1. It's going to end at 13. I'm just going to do one period. I'll show July, April, and October. Okay. The Y values I really, really want labeled are the max, which I know at 92, and the min, which is 63.8. And we started right down here in January. Hit the max in July, back to the minimum there. October and April were about halfway in between. And there, more or less, would be one period of our weather data for Tallahassee.